Hello, I'm Austin Proby, Emergent Space Technologies Director of Research and Development, and today I would like to talk to you about GEAR, or the Generalized Environment for Application Reuse, which is our approach for MOSA agnostic flight software development. Just a brief overview, we'll go over the background, why we built GEAR, talk a little bit about the GEAR concept, go over the use cases that we're building out for GEAR, talk a little bit about our implementations of different MOSA systems, and then touch on Yeti telemetry management for GEAR. Although if you'd like more detail on what we're doing for telemetry management, we have another presentation on Yeti at the workshop, and then wrap up. So Emergent has been developing flight software for about a decade, starting back with DARPA System F6, and we've always come at it with a MOSA approach. We have multiple different flight software components that meet various different needs for flight software autonomy, things like autonomous GNC, spacecraft control, fault detection, isolation, and recovery, resource-constrained cloud computing, and autonomous multi-agent management. And we have interfaces for spacecraft buses and payloads. So most of flight software development is something we are very familiar with. When we have developed flight software, we've noticed a few challenges. A variety of government customers and prime contractors have different platforms or MOSAs where they want the flight software to be developed and deployed. One customer may even want different deployments, different implementations of the same capabilities over time as they change what they're using internally. And while our own software is built to be portable, the adaptation layers vary based on the MOSA, and it takes time to do that implementation. And there's some non-recurring engineering associated there. Also, we've noticed that writing glue code or code that adapts the core functionality to different platforms is very repetitive and error-prone. Our original approach for dealing with MOSAs was to determine which MOSA was best. We have been using CFS, NASA CFS, since DARPA System F6, so that's kind of been our default option, but we had an opportunity to sort of reevaluate based on beginning of a new contract where we were kind of building out MOSA infrastructure, and we sort of took a traditional engineering approach and did a trade study of the available MOSA systems to determine what was going to be the best to suit our needs. We looked at a few options, including CFS, ROS2, SSM, and Aspire. And the outcome of this trade study was that there wasn't really an outright winner. And our MOSA selection has really been driven by a project need basis. We've stuck mostly with CFS because that's what we've used the most. But we have had to implement multiple different other MOSAs based on the contract. One thing the trade study also demonstrated to us, though, was that there is significant commonality between the different MOSAs. They are essentially all application layers with abstractions for message-based communication. And to illustrate that, I have some architecture diagrams from various MOSAs that we looked at. CFS, this is something that many people at the workshop are familiar with, has its OS abstraction layer, and then it has an API that applications can use to send messages around to have run timings interface with CFS. ROS2 is similar. There are middleware bindings that map to GDS, which is the messaging system that ROS uses on the back end, and then there are client API interfaces that allow application code to access those lower level interfaces. Aspire is similar. There's mission applications that use the Aspire APIs and have a platform extraction layer at the base that sort of abstracts away the lower level system interfaces. And note this realization that they all sort of have a similar message-oriented approach to flight software development, and mission efforts that demonstrated that we need compatibility with other MOSAs based on customer needs made us realize that we needed a multi-MOSA framework for our flight software. And that is going to maximize the portability of Emergent's flight software applications and decrease the amount of non-recurring engineering that's required for new applications and adding multi-MOSA support to those different applications. So the objectives of our flight software agnostic system that we wanted to build was to have a generic architecture for our applications that can be deployed on a variety of software platforms. We'd like to, and we're focusing on message-based communication systems, these MOSA message-oriented middleware. We want to have a well-defined, easy-to-use environment for developing flight software that can be consistent for developers. And we want to have rapid development using state-of-the-art development tools, software modeling, and code generation technology. And that led us to the GEAR concept. GEAR is a MOSA agnostic framework for space applications. It allows for significant reuse of code without development, moving applications between MOSAs, and it's intended to meet the need of higher-level flight software applications. So we're not building something that's doing low-level RTOS interfaces with reaction wheels or firing thrusters. It's really for high-level applications because Emergent flight software tends to address sort of higher-level autonomy, planning functions, and that's where it tends to live, not at that lower bus level control. And this is the general layout of GEAR. It's actually very similar to the architectural diagrams that you saw with the MOSAs. There's an adapter layer that, instead of adapting to the lower level abstraction that the MOSAs do, adapts to the different MOSAs. And above that, there are mission applications that have consistent interfaces to operate with different MOSAs. And the goal of the framework, again, is to reduce cost and development time for moving our existing applications between MOSAs and just reduce the time for developing new applications as well. A little bit about our previous approach to building our previous flight software framework. We had a three-level framework for developing flight software. We had a service layer where sort of the core functionality of a flight software application existed. There's an adapter layer and an application layer. The core functionality, the heavy lifting, is all done inside the core service, and that service was portable. And in that way, this architecture did support portability. But every time we had to implement an application for a new MOSA, the adapter layer had to implement the service calls in a way that was compatible with the new MOSA. And then the MOSA application layer is how you actually sort of spin up the application, initialize, do your subscription at a low level, start your interactions with the MOSA, and kind of start the main program loop. And in the GEAR framework, we've kind of changed that, essentially the structure of our applications. We have a GEAR base adapter that is implemented and defines the GEAR functions and how the system operates. And we have a MOSA-specific GEAR implementation. So what that means is that for every MOSA, there's a set of APIs that are defined at the base GEAR adapter that are then implemented for that MOSA in this MOSA-specific implementation layer. And we have our core services and our adapters, but in this case, our adapters are using the GEAR APIs instead of the different MOSA APIs. And because GEAR has derived implementations for the different MOSAs that we're using, we don't have to re-implement this adapter layer for different MOSAs. We just have to make sure that there is a MOSA implementation of the GEAR APIs. And then we have our MOSA-specific application layer, and we've tried to build that out in GEAR so that it can really be implemented once and just configured for your different applications. And this structure, while it looks a little more complicated than the previous one, definitely does sort of reduce the NRE required to move the applications between MOSAs as long as an implementation layer exists. And if it doesn't, all you have to do is build that new implementation layer, and your existing applications will be compatible. GEAR is built on a sort of a superset of API calls that are provided by these MOSA middleware, things like application initialization, execution, message subscription, sending, receiving, things like that. And then we have GEAR APIs that we've implemented for simplification or to handle incompatibilities for things like timing, logging, file handling, and application configuration. So this is sort of the basic anatomy of a GEAR SpaceApp, which is our term for our applications. There are message definitions. There's a service message implementation that is how we define the messages for our applications and send them around. We have a service model that is a sort of a basic implementation of a service that describes how all of our core services are implemented at a high level. and then that service model is specialized for each different application in the implementation of its core service. We have pub/sub messaging sort of at the core of everything, and then we have implementations of those that pub/sub messaging for the different MOSAs in these different MOSA-specific implementation layers. Currently, we have implementations for the core flight system, CFS, and we have a 0MQ test system that's really intended just for quick development and test. We have an alpha implementation that we're building out for ROS-M. There's been a significant investment in ROS-M from the DoD, especially on the robotics side, and we have customers there in the DoD, and they're very interested in having us build this out. And we're also planning on building an implementation for Ascent, which will allow us to embed our flight software into Emergent's modeling and simulation framework for scalable, fast and real-time testing, which would be very nice. Just a sort of a low-level example implementation of what gear looks like what it looks like in the code. We have gear definitions that define what functions are available for different applications, and those definitions are constant across all of the gear MOSA implementations. The applications can then use those definitions, and then when you build your gear application for a specific MOSA, then the MOSA implements the back end of that call as it is required for that MOSA to support its back end implementation. So if you build the ZRMQ version, it uses this send for gear ZMQ, and if you are building a CFS version, it sends this way for CFS. In that way, the application code doesn't have to change, and you can move into different MOSAs. Some key use cases for gear are really broken down into two categories. We have interactions with the developer, things involving deploying space apps, starting deployments, running applications, and then real-time interactions with the space apps themselves, things like subscribing to topics, transmitting messages, checking for messages, and requesting the current time and file read and writes. And gear provides constant mechanisms for accessing these functions in different middleware so that our applications can do these things the same time every way, which is really nice and saves really enables this kind of portability that we're seeking. And this is currently a initial subset of the functionality that we've implemented with gear, and are looking to add more use cases as the development advances and we need more capabilities out of the system. One other key feature of gear is that we want to have automatic telemetry management to handle things like flight software messages, ICDs, payload interactions, and ground system definitions and pages. Gear achieves this by using two emergent products, Fractal and Yeti. Fractal is our sort of code generation backend. It's a tool for taking code and then describing that code as a set of abstract syntax trees that can then be used to generate or render new code. And Yeti is a implementation of Fractal to manage spacecraft telemetry and definitions. And that is what we've implemented in Gear. So the workflow for Fractal is you have some initial C++ code or some other kind of definition like a YAML that can be imported by Fractal and turned into this abstract syntax tree, and through various processing nodes you can generate new material, different language code, different artifacts, different message types, ground system pages, etc. And Yeti is sort of an implementation of Fractal for the case of flight software telemetry. It's a Python API that can import project ICDs or header files, and then can generate these syntax trees and then use that to build up both message definitions and interface code to adapt to different flight software, or adapt those messages to different flight software implementations. and it can also implement things like middleware bindings, static allocation tables, and message buffers, essentially all the boilerplate that you need for your application in your different MOSAs. For essentially what we're doing is we are taking this message definition and using it to generate message classes, structures, and application adapters for the different MOSAs, all automatically based on this telemetry definition. And we do this with Yeti instead of doing it manually, because previously we had developers had to spend a lot of time focusing on building this glueware, and this allows us to develop new flight technology instead of writing this glueware to tie different applications together in what has traditionally been a very error-prone process. We also have a lot of sort of advanced development tools to support Gear. The key being our Docker-based SDK enables native editing for Gear applications and container-based compilation. So we have pre-configured tools and tool chains all contained in these Docker containers that can quickly be deployed. It's cross-platform. Anywhere you can run Docker, you can run the SDK, and it allows us for rapid deployment. Previously, we used sort of provisioned VMs for our development environments. So developers had to build applications in the VM or with shared folders, which can be kind of a pain. And the system was slow. There weren't that many resources available, and whenever the VM got messed up, it took hours to days to rebuild the VM based on sort of how your VM was initially configured. But with Docker, we can configuration manage our development environment and just pull down a new one, and that time is really just limited on your network connection speed. So we can go from nuke your development environment and start over in a matter of minutes, which is fantastic. In conclusion, we are moving all of Emergent's flight software products into Gear. So that includes the cluster flight application, our autonomous navigation suite, Cirrus, our suite for resource-constrained cloud computing, Safer, our fault detection, isolation, and recovery suite, and Dasher, or multi-agent autonomous executive. And we're putting all these things together to provide a modular suite of flight software with different capabilities. Gear will provide significant advantages. It produces reusable code and reduces non-recurring engineering. It also uses in conclusion, we are building Gear and moving all of our flight software into Gear. That includes our cluster flight application, Cirrus, our resource-constrained cloud compute environment, Safer, our fault detection, isolation, and recovery suite, and Dasher, our multi-agent autonomous executive. We are putting all of these things together into a common Gear-based suite, and this is going to provide a modular, portable suite of flight software that can provide significant autonomy capabilities. Gear is going to provide significant advantages for flight software development. The main one being reusable applications. Our previous CFIS and Cirrus adaptation layers didn't seriously intend for reuse or productization, and Gear is designed specifically to enable that. We're using advanced code generation technologies with Yeti that include message structures and conversion, serialization, deserialization, ICD generation, ground system integration, and that is much better than having to do that by hand, which was our previous approach. And it's going to provide a reduced learning curve for our developers, because we have a common flight software framework and straightforward interfaces that are intended for new users to pick up quickly. And this is what our goal, to have all of our main flight software applications together running Gear and talking to each other, enabling new capabilities that we can deploy going forward to solve new problems in flight software. And we think Gear is a key enabler of this capability, and we are pretty excited about it. That is all I have. Feel free to reach out with any questions.